were together doing this, we talked about substitution. Well, problem 2, 7.1 number 2, says solve graphically. Obviously, the presence of that logarithm in there kind of limits us in terms of substituting or something. So we're going to solve by graphing. You got a couple of different options. First of all, I don't know what mode you're in, but you got to get back in function mode. Everybody okay with that? And we're going to put in our equations, ln x and x squared minus 4x plus 2. I'm going to use a standard window to start. So my window is a mess from all the parametric stuff and all that. So I'm just going to go with a standard window. And I'm going to graph this. First of all, do you recognize the two shapes that you got? We know what ln x looks like, and you know what an x squared looks like. So you should have gotten those two. How many places do they intersect? 2. So you remember how to do that? Second calc, intersects. You can only do one at a time, so you got to figure out one of them. Shout it out when you get your points of intersection. That's what we're looking for. Fisher, what are you doing? Huh? Function mode? I would never yell at you. Ha 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 ha. Function mode. All right, anybody getting any points of intersection? What'd you get, Charles?
0.71, negative 0.34 for x and y coordinates.
All right. Notice how he's answering, because anytime we're looking for points of intersection, they're points, right? You got the second one, Charles, or not?
Yeah, 3.83 and 1.34.
Anybody have a question about either one of those? Everybody remember how to do things graphically? All right. Next step, elimination. This chapter is all about solving systems of equations and inequalities and all the different techniques that we have to do that. So we're going to be learning some new ones, but this one isn't new. This is old. How do we eliminate? If we have to use elimination, directions say use elimination. What do you want to do here? You want x's or y's. X's would be handy because one's already positive and negative, but it really doesn't matter. You just have to make one of the letters, either x's or y's, be eliminated, cancel out. So to make that happen, we got to multiply the top one by 3 and the bottom one by 2. And remember, when you do this, let's not make careless mistakes. This is easy stuff. We should be rocking this. When we do it, we got to go all the way across. So 19y equals 57. Oh, another nicely rigged problem. Y equals 3. And then what do? We're not done. Remember, your answer must look like this. So what do we need to do? Plug it in anywhere you want. Doesn't make a difference. Plug it in somewhere. So 2x plus 9 equals 5. So 2x equals negative 4. I got x equals negative 2. So my answer is negative 2, comma 3. With me? You're thinking, oh, this is so easy. You're right, it is. All right, another one. All right, here we go. We're going to eliminate here. the top one by -2, actually. Don't we need to do -2? -2. On this side, all I have left is 0, don't I? And on this side, I have 8. If I multiply right, does 0 ever equal 8? That means these two lines do not ever intersect, which means what? Describe them to me if they don't intersect. These are parallel lines. These are parallel lines. There is no intersection, right? No intersection if they're parallel lines. Everybody okay? That can happen graphically. You can get parallel figures that don't cross. It could happen with substitution. It doesn't matter how you solve the system. If they're parallel, they're parallel. And you're not going to get an answer. And you know you're not going to get an answer because you get something that's false. All right, now look at the next one, because the opposite is going to happen. I think we may have talked about this last time. Can't remember. We multiply the top by 3. What's going to happen is a little bit different this time. If I multiply the top equation by 3, I get 0 equals 0. Is that ever true? It is always true. Now, I think we talked about this the other day. You cannot say all real numbers, because that isn't where these two lines intersect. These two lines do not intersect everywhere. Where do they intersect? On the same line. This is the same line. So if you were interested in formally writing a solution, you would say something like, okay, the answer is the set of all ordered pairs such that 4x minus 5y equals 2. That's the actual answer, because you just told me that it's all of the ordered pairs that are on the line, and that's the way you would write that. Does that make sense to you? These are the same line. So instead of having no intersection at all, they have infinitely many, but don't say all real numbers, because that's not right. All right, to show you that we can have systems of equations in word problems, and they are just as easy. A couple of examples here. They're just as easy. In fact, the first one, it talks about Nybach manufacturing, making new tennis shoes. Says we're looking for the equilibrium point. Who's an econ or has had econ? What do we mean by the equilibrium point?
Well, I was very going to hand the answer that I was going to need now.
Come on, the equilibrium point.
Where the points are equal.
Where supply equals demand. That's called the equilibrium. If supply is greater than demand, you got a factory full of stuff waiting to be sold. If demand is greater than supply, you don't have enough stuff to sell. In a perfect world, equilibrium, it's all balanced out. You got exactly the amount that you need to sell. So, if demand has to equal supply, won't we just set these two things equal to each other? All right, let's solve it. Keep an eye on my arithmetic. I got x equals 5. And if x equals 5, then p, which is the y variable this time, is 135. Now explain that solution. Okay, so the equilibrium point would be 5, 135. What does that solution mean? Is that?
If each pair costs $135, then you'd still sell 5 million.
Exactly. X is in millions, so I'm gonna sell 5 million pairs of shoes if the price I choose is $135. All right, oh lordy, another airplane flying with the wind from Los Angeles takes this long, flying against the wind, it takes this long. If the air distance is 2,500 miles and the airplane speed and wind speed are constant, find the speed and the speed. Now, this problem is a first-year algebra problem, so it isn't as sophisticated as the ones that we have been doing. There's no directional, we don't know the plane is flying on this course, the plane is flying on that course, the wind is blowing, whatever. We don't have any of that information. So with the wind and against the wind means whatever direction the plane is going, the wind is going in exactly the same direction. And against the wind means whatever the direction the plane is going, the wind is coming at it exactly from the opposite direction. Are you okay with that? Okay. So if I'm the airplane flying at a speed of, well, it doesn't tell me, so I'm gonna say X is the plane speed. If I'm the airplane and I'm flying X, and the wind speed is W, and we're going in the same direction. In other words, I'm with the wind. What will my speed be if I am with the wind? Won't it be X plus W? And if I'm against the wind, it will be X minus W. Does that make sense to you? Okay, so now we need to rely on a piece of knowledge that we learned a long time ago in first year algebra, way before. Distance equals rate times time. So if I'm going 10 miles an hour for 2 hours, I would go 20 miles, right? We know this concept. Now, do I know the distance that I am traveling with the wind? I'm going 2,500. All right, so I'm going, my distance is 2,500. My rate with the wind is X plus W. And my time with the wind is 3.75. Does that equation make sense to you? All right, what's the corresponding one? Against the wind. What's the distance against the wind? Same. My speed against the wind is X minus W. And my time against the wind is 4.4. What do I have up here on the board? I have a system of equations. So let's take 2,500. Again, you can do this however you want, but I'm going to take 2,500 and divide it by 3.75. And I'm going to change that into a fraction. So I have 2,000 curves equals X plus W. I took 2,500 and divided it by 3.75. Does that make sense to everybody? And then I'm going to do the same thing. I'm going to take 2,500 and divide it by 4.4. Change that into a fraction. And it's 6250 over 11. Now, at this point, if this would be easy to eliminate, right? And with my calculator, I'm not gonna worry about this horrible arithmetic. We'll talk about other options here in a minute. But when I add, I'm gonna get 2x equal to those two added together. Which is 40750 over 33. So x will be this right here divided by 2. So half of 40750. I should do that on the calculator. So I got 20375 over 11. Oh, over 33. Which is 617.42 miles an hour. So the plane is flying, unless I made an arithmetic mistake, the plane is flying that fast. How do I find the speed of the wind?
Plug her on back in.
Plug her back in, that's right. Let's see, where am I gonna plug back in? Maybe I'll take 2,000 thirds and subtract x. And I got the wind is 49.24 miles an hour. David?
Would it be like negative? I mean, it's not obviously negative speed, but like just going the opposite direction.
In this problem, the wind and the plane are non-directional. So it wouldn't be opposite direction, except when I was going against it. It would be positive, the same direction, the other way. So no, we don't put a sign on there, this is speed. This is just speed. Speed is a scalar, so it's not directional. Okay? Now, back here at this point, if you really didn't want to mess with these fractions, you could have multiplied by 3 and multiplied by 11, and then like done regular elimination or something with it, if you wanted to. But these are the equations that you set up. That's the important part. Everybody okay with these equations? All right, 7-1 is done. That homework will be due. We have school.
After Jesus is risen.
Yeah, so Jesus has risen. Yeah, be Tuesday. All right, so this is due, your homework is due 7-1 is due on Tuesday. All right, 7-2 is a monster, but luckily it is easy. Did you guys last year have the opportunity to discuss matrices at all? Did any work with matrices? Don't think so. Now, that's not surprising, because that's a couple of school years where we haven't gotten much done. So let's talk about what a matrix is. I'm going to give you an example. I'm just making this up. That's a matrix. A matrix is a rectangular array of numbers arranged in rows and columns.
It's like a
Columns, how about we start there? A rectangular array of numbers arranged in rows and columns. That's a matrix. So, you see how that definition fits with my example? The dimensions of the matrix are the rows by columns. So rows are like the bleacher. Rows go this way. Rows of the bleacher. Columns of the White House. So this matrix has dimensions 3 by 2. This is pronounced or said 3 by 2. It has 3 rows and 2 columns. So this is a 3 by 2. Matrices can be any size they end up being. This one happens to be 3 by 2. The numbers inside the matrix, these guys right here, are called entries or elements. Either word is fine. So these are the entries in matrix A. If a matrix happens to have the same number of rows as columns, it is called a square matrix. Just like if a room is 12 by 12 or 15 by 15, if its dimensions are the same, it's called a square room. A rectangle is square if its dimensions are the same. Square matrices are special in the study of linear algebra. This is called linear algebra. Square matrices are special. We can do stuff with square matrices that we can't do with other matrices. We're going to find out what we're going to get. A little bit of notation here. If it's going to come up in one of the later problems. If I want to talk about, let's say this entry, right? Oh, that's not a good choice. If I want to talk about this entry right here. Since he is in matrix A, I will use a lowercase a. A means the matrix. Lowercase a names the numbers in it. And I would say that is the entry that is in the 1, 2 spot. First row, second column. In matrix land, everything we do will be rows, first, then columns. So the dimensions, 3 rows, 2 columns, 1 row, the first row, second column. Roman Catholic, rows, columns. What do you think equal matrices are? Let's get some vocabulary down here. What do you think equal matrices are? Throw out some ideas, Charles.
Matrices with the same dimensions.
Okay.
Matrices,
Same dimensions.
of rows and columns.
Okay, now let's think about that for a minute. So Charles, let's look at this matrix and this matrix. Do these two matrices have the same dimensions? Yes. They are not equal. You do have to have the same dimensions. You have to be the same size. Absolutely. That's part 1. But what's part 2, David?
The same numbers.
Okay, let's look at that. So let's take this one right here, and how about this one? Would you say these two are equal, even though they have the same dimensions and the same numbers? Are they equal? No, there's another piece to it. Not only do they have to have the same numbers, but those numbers have to be in the same spots. So the way we say that is, equal matrices have the same dimensions and the same corresponding entries. Same dimensions, same corresponding entries. Matrices can only be equal if they have the same dimensions and the same corresponding entries. That means same numbers in same spots. All right. Transpose. The transpose of a matrix, I'm just going to use that as my example. The transpose of a matrix is denoted with the superscript T. That T can be capital or lowercase. I mark them with a capital, but I've seen other people mark them with lowercase. It doesn't matter. If you have a T up here, that means transpose. The transpose of my matrix is this. What did I do? Interchange the rows and columns. So what was row 1 is now column 1. Row 2 is column 2, and so on. The transpose simply interchanges rows and columns. And there are matrix operations that require the transpose. What are the dimensions of A transpose? Well, if A is 3 by 2, then obviously the transpose is going to be 2 by 3. A scalar. Well, we talked about scalars in the vector unit. What's a scalar? Just a real number, right? It's just a real number. Kids, there's a ton of overlap between vectors and matrices because if you think about it, this is just 3 vectors put together, right? So a lot of the vocabulary is the same and a lot of the operations are the same. Identity matrix. The identity matrix is associated with square matrices. If you're in if it's a 2 by 2, this is the identity. If you're a 3 by 3, this is the identity. And so on. Now, the easiest way I can make a connection to what you already know is, what vector is this? I, and this is J. So the identity matrix is composed of the standard unit vectors. In 2 dimensions, it's I and J. We did not discuss this, but in 3 dimensions, it would be I, J, and K. We didn't talk about that, but that's what it is. The identity matrix is composed of the unit vectors. So it looks like this. You could build the 4 by 4 one, the 5 by 5, they're all structured just like this. One's on the main diagonal, and everything else is a 0. That's the identity matrix. Non-singular versus singular. I'm going to give you the definition, but it's not going to mean anything right now because you don't know what part of the definition means, but you will. This is just vocabulary. A singular matrix has a determinant of 0. Determinant. A non-singular matrix then has a non-zero determinant. We'll see what the implications of that are when we, number one, figure out what the heck a determinant is, and then we'll see what happens when it's 0 versus when it's non-singular. No, singular is 0. Non-singular is not 0. The trace of a matrix, well, I can't do it with this one. To have a trace, a matrix must be square. So that's the first rule, gotta be square. And then, let me put a square one up here. Let's say this is matrix B. 1, 5, 7, -2. The trace of B, and that's denoted with a TR out in front, means the trace of the matrix, is this the sum of the entries on the main diagonal. So that would be 1 plus -2, the sum of these guys right here. So the trace is -1. Now, I'm going to give you the formal definition. This is how you find it. You just add these numbers right here. If it's a bigger matrix, you would add all these. So the trace of this one would be 3. It's got to be squared. So your formal definition is this. If A is n by n, trace A equals A sub 1, 1 plus A sub 2, 2, all the way to A sub n. Does that definition make sense to you? If the matrix is n by n, that means it's square. What's the 1, 1 entry? First row, first column. Isn't that right here? What's the 2, 2 entry? second row, second column, isn't that right here? And then you got the 3, 3, the 4, 4, the 5, 5, all the way to however big it is. That's the trace. Now, with all that vocabulary information, and I'm sure there's some I forgot and we'll have to add in as we go, we should be able now to do some of these problems. All right, so let's look at 2A. What are the dimensions of matrix B?
2 by 3.
The dimensions of matrix B, 2 by 3. Why? 2 rows, 3 columns, right? C sub 3, 2. Now what does that mean? That means look in matrix C and find the entry that is where? Row 3, column 2. So in matrix C, row 3, column 2, the answer is 3. Count down. Everybody got row 3, column 2? That's a 3. A plus D. All right. Take a wild guess how we're going to add these, and you'll be right. It's the only logical way. Add the 1 and the 2, and the negative 2 and the 1, 3 and the negative 5, and the 4 and the 3. Does that make sense to everyone? Okay, so let's talk about how we add matrices. Do you think every set of matrices in the whole wide world can be added? No, what has to be true about them? They have to have the same dimensions. They have to have the same dimensions. You can't add unless they have the same dimensions, because the only way to have entries match up like this is if they're the same size. Now, they don't have to be square. That's not a rule for addition, but they do have to have the same dimensions. So if I had 2 3 by 7s, I could add them. But if I had a 3 by 7 and a 7 by 3, I could not add them. All right. A plus B, no solution. Can't do it. The rule is very strict. Can't do it. No solution. D minus 2A. Well, what do I do with 2A? Right here, what's that mean? Well, how am I going to handle that? Multiply everything by 2. It's a big distributive problem. And multiply everything by 2. So that's going to be 2, negative 4, 6, and 8. Everybody okay with that? Now, I got to subtract. So I'm going to subtract the same way I added. So 2 minus 2, 1 minus negative 4, watch your arithmetic, negative 5 minus 6, and 3 minus 8. Is that okay? All right, get ready to have some fun, because now we're going to multiply. And the rules for multiplication are different than the rules for addition. Remember, to add matrices, they have to be the same size. To multiply them, here's what has to happen. You just count it down. All right, to multiply them, here's the rule. Write down the dimensions of the first matrix. So what are the dimensions of this guy? dimensions of the second one,
2 by 3.
2 by 3. If you're gonna multiply, these two have to match. And then the answer will be this. So when I multiply these, I am gonna end up with another 2 by 3 matrix. Okay? Now, how do I get those numbers? Well, it's sort of like a vector dot product. In fact, it is a vector dot product. But the vectors that you're multiplying, to fill this spot right here, which is row 1, column 1. Row 1, column 1. So you're taking the numbers in this row and you're multiplying them by the numbers in this column, and then you're going to add them together. So remember how the dot product, you did first times first, second times second, and added them up? That's exactly what you're doing. Only one of them sideways and one of them's up and down. So that first number would be -7. The numbers in the first row are 1 and -2. The numbers in the first column are 1 and 4. So there we go. Now, how do you think we're going to find this number? First row, second column. So we're going to take the numbers in the first row, which are still 1 and -2, but we're going to multiply them by -1 and 0, and then add the products. So it looks like that one is -1. Okay, you think you got it? All right, go ahead and fill in the rest of them. I'll do it too, we'll compare answers. Are you matching? You look okay? Anybody have a question about any of those numbers? Anybody not sure where they came from? All right, we're going to multiply again. We're going to do B times C. Before I get it all written out, let's figure out if we can do it. So what are the dimensions of B? 2 by 3. What are the dimensions of C? Can I multiply?
Yeah.
Yep. Unfortunately, here we go.
That's good though.
That's good.
More math.
More math, more practice.
Yes.
So you said 2 by 3 and 3 by 3. So indeed they match. And this answer is going to be another 2 by 3, right? This is going to be more numbers though. I mean, same number of answers, but now when I multiply row 1 times column 1, it's like doing a dot product of 3-dimensional vectors. So I have to take 1, -1, 1, and times it by 1, -2, 0. Did you get 3? exactly the same, it's just bigger. So now this one times this one, go ahead, I'll shut up, you go ahead and see what you come up with. Try not to miss any of these, but I probably will. We okay? Oh, there's one of them wrong, which one?
At the top it was 3.
This is supposed to be 3.
I'm not
No. Let's just check it, so top row, then 0, 1, 3.
Oh, I wrote it down.
Okay, you all right? All right, next page, here we go. Oh, what do you think a squared means? Multiply it by itself. Now, let's talk about that a minute, Wayne. Can I square any matrix in the whole wide world? Can I? Think about it. What if it's 2 by 3? Can I multiply a 2 by 3 by itself? No, the only way I can square them or cube them or do any of that is if they are squared. They have to be squared. Does that make sense to you? You cannot square them, multiply them times themselves, unless they are squared. Well, luckily A is squared. I mean, literally A is a square matrix. So we can square it. So let's do that. What is A squared going to be? All right, go ahead, let's see what you come up with. This is my God, but I don't know. All right, we just did BC. This last question here says, what's CB? Well, can we do CB? Wait, what are the dimensions of C? 3 by 3. What are the dimensions of B? 2 by 3. All right, now wait a second. We did BC. BC worked out for us. CB can't be done. What does that tell you about matrix multiplication and commutativity? Real numbers are commutative. 2 times 3 is 3 times 2. What about matrices? No, not commutative. Order is extremely important. Order is extremely important when you are multiplying matrices. All right, one more in this little part. are we going to prove that these two are inverses? All right, now wait a second. Let's think about what it means to be inverses. These are additive inverses because when you add them, you get the additive identity. 0 is the additive identity because when you add 0, it doesn't change anything. In multiplication, 3 over 2 times 2 over 3, these are considered multiplicative inverses because when you multiply them, you get the multiplicative identity, right? So what it means to be inverses is they cancel each other out and you get the identity for whatever operation you're doing. Well, if these guys are going to be inverses, then what should happen when I multiply them? What should I get when I multiply them? The identity, right? Let's see if it happens. Let's multiply them. And this better be a 1, 0, 0, 1. Okay? Let's see if it is. Oh boy, it's looking good. I think they are inverses because when I multiply them together, I got the identity. It's no different than when you multiply a reciprocal. You get the identity. It's the same thing, only you get a big matrix. Okay? Everybody all right? Soon we're going to learn how to find the inverse. But you just proved these two were inverses by multiplying them. All right. Take a look at the next section. I know what you're thinking. I want you to shut up. No, we have a lot to do. So no shutting up today. We're going to keep plowing ahead. Okay, so the notation looks like absolute value. In vector land, it was magnitude. But in matrix land, this is the notation for that thing we call the determinant. You can only find determinants if the matrix is square. This is square, so I'm good to go. I'm going to find the determinant. Here's how it's done. It's a number. Just like the magnitude is a scalar, the determinant is a scalar. So you take 1 times 1. You take 6 times -3. And then here's the kicker. You subtract them. Well, I have to keep straight here. But it's 1 minus -18. So the value of the determinant is 19. 1 minus -18. Do you see how it's possible to do that operation and get 0? That would mean your matrix was singular. This one is not because the determinant was 19. Okay, do the next one. What is the determinant of B? These vertical bars mean determinant. The determinant is a number. So the number this time is 8 minus 0, or 8. Everybody got 8? Now what about C? No can do because it's not square. So I will try to trick you. Don't be tricked. if it's not square, so far, we've talked about, if it's not square, there's no identity for it, there's no determinant, and there's no trace. And you can't square it or cube it or something like that. All right, now look at D. Oh boy, it's a little bit bigger. Now, there are two different ways to do this problem. I'm gonna go through it one way, because I think it's the quickest, fastest way. But then when we get to the 4x4, which is F here, when we get to the 4x4, we'll talk about how the strategy for a 4x4 can be used on a 3x3 also. But I think this is the easiest way. You'll decide how you do it. Take the first two columns and write them down right outside the matrix. So column 1, 1, 3, 0, column 2, negative 1, 1, 1. There's a lot of arithmetic involved with all this matrix stuff. Keep track of your negatives. Now, do you remember how on this one, we started right here and we multiplied these together? I want you to start same place, and I want you to multiply those those three numbers together. And I'll get negative 4. Now, step over and multiply these together. You get 0. Multiply these together, we get another 0. Total those up. So I did this diagonal, and this diagonal, and I totaled them up. Just wait. Now, you're going to go the other way. Remember how you multiplied this, and then you multiplied this? So now you're going to start down here. You're going to multiply those together, and you're going to get 0. You're going to multiply these together, and you're going to get 2. And you're going to multiply those together, and you're going to get 12. And you're going to total those up. Okay? Now, let's think about what we did over here. We did this one. We did this one. And then what did we do to those two numbers? Subtracted. So you're going to take your downs, which were negative 4, and you're going to subtract your ups, which were 14. So the value of this determinant is negative 18. Now, let's see if you learned anything. Can you do E? It is the same thing. You're going to do it the same way. So I'll get it set up, but then I want you to actually do it. So copy down those first two columns. And then where do we start multiplying? Always, 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 we start right here with the first number. Okay, did you get negative 10 for this fraction? did you get 77 for this direction? So what did you get as your final answer? Yep, negative 87. Perfect. All right, that's what? What, negative 87? Okay, what's your favorite number? Okay, all right, we don't have near time enough to do problem F, so I'm gonna stop right there. I know, bummer.